Hello, everyone. Welcome. So this is our June lecture. It's the final lecture in this lecture series, but as you may have seen up at the door, the schedule for the next 6 months is now available. I haven't yet put together the titles and the speakers, but they'll be available in the next few weeks. They'll be posted on the website that's at the bottom of this flyer. So you're welcome to come back. This is a monthly scheduled event where we, if this is your first time, we have a roughly 30-minute lecture followed by questions, and then you're welcome to either stick around here and we'll have a panel Q&A with a number of astronomers and astrophysicists to answer your questions on a variety of different topics, as well as we'll have telescopes set up outside that you're welcome to view through at various different targets. The weather looks pretty good tonight. We aren't expecting any clouds, although because we're pretty close to the summer solstice, it's getting dark later and later, and so it's still kind of bright, but sun set about 4 minutes ago and will continue to get darker. So in about 30 minutes it should be dark enough to be able to see the moon and Jupiter and a globular cluster and maybe Saturn at the end of the night. So there will be a number of things to see. But you're welcome to go back and forth in between here for the panel Q&A and the observing until 10 o'clock when we finish up. So in addition, we have events called Astronomy on Tap at a local bar once a month. Our next is a week and a half from now. It's June 12th, where we have 2 15-minute informal talks in a bar, so you can be drinking beer or what have you. And it's pretty fun. So I encourage people to come out. We have more information about those events on our website as well, outreach.astro.caltech.edu. And those, as I said, are monthly as well. In addition, let's see, there's going to be the solar eclipse that's happening in August 21st. That will not be a total solar eclipse from here in Southern California, but you'll be able to see a partial eclipse, which is still going to be pretty cool. So we're planning to have some events available here to be able to see through a telescope or through special glasses that don't damage your eyes. When you look at the sun, then you can see the disk of the sun covered up partially. I think from here it's about 70% coverage by the moon over the face of the sun. So that should be pretty spectacular. But again, don't worry, that's 2.5 months away. A quick reminder that when you go on the field, it's a new artificial turf field, and we've been given strict instructions that you can't have food or drink or cigarettes or pets or high heels even on the field because it can damage the field, and then we don't get to use the field anymore. The athletic director was very specific to me. So please abide by our instructions, and you'll have a great time out there. I think that's it for announcements. Our speaker for tonight is Ivanna Escala. She's a second-year graduate student here working on chemical enrichment of galaxies. She did her undergrad at UCSD before coming here, and we're all really happy that she's joined us tonight. So please welcome Ivanna Escala.
Hello, thank you for coming, everyone. So today I'll be talking about the origin of the elements, as in the elements that we know from the periodic table. So when we look at the universe around us, you'll notice that we have an extreme diversity of elements, but how did these form and where did they come from? So you'll notice that these elements are just not forming left and right around us on Earth. So that's suggestive of the fact that it requires very specific conditions in order for these elements to form. So the formation of new nuclei is known as nucleosynthesis, or new elements, and it requires very high densities as well as high energies, and so comparatively extreme environments compared to what we know here on Earth. So if they can't form here, the only other place that we can really look to is the stars. So when you look at space, you see structures of this form. You see these beautiful gaseous nebulas. And what these are hints of the existence of these astrophysical laboratories in which these elements are made. They're remnants left over from extremely high energy events like supernovae, which many of you may know about. So they're able to achieve these energies that are high enough for fusion to occur. So we have the light elements that were actually created very early on in the universe in what is known as Big Bang nucleosynthesis, and then all other elements are created in processes related to the evolution of stars. So I'll be talking about where these various different groups of elements come from. So when an astronomer looks at a periodic table, they may see something that looks more like this, as compared to when a chemist looks at a periodic table, and they may think about, right, certain chemical reactions that result in certain compounds, or when a physicist looks at a periodic table, and maybe they're thinking really in depth about electronic structure. But when we look at this, we see certain things that formed in the Big Bang, certain things that have formed in larger stars, certain things that were formed in supernovae overall. So we call all elements that were formed in stars by the name of metals. So everything that is not hydrogen or helium is characterized as a metal. So metals are a very small portion of the universe as a whole, but they're extremely important for life. Of course, we're carbon-based organisms, so we could not exist without all of these processes related to stars that end up creating these metals that are then incorporated into our bodies. So metals did not form initially after the Big Bang, since the conditions in this expanding universe that was initially still very hot and dense were not right. So first, we'll go over a history of the universe as a whole. So right now, we live in the era of galaxies, in which the universe is actually pretty cold, and we have these large structures known as galaxies, very large collections of gas and stars, and also dark matter and the like. Very early on in the universe, things were pretty strange. It's mostly in the realm of particle physics, so we're not going to talk very much about that here. But things were extremely hot, and you didn't even have, say, the formation, you didn't have protons or neutrons that existed initially. But eventually, a few minutes after the Big Bang, you end up having something known as the era of nucleosynthesis, in which, as the universe continues to expand following the Big Bang and gradually cools and reaches temperatures around 1 billion degrees Celsius, the conditions are right for the formation of hydrogen and helium. So these were the first elements that formed shortly after the Big Bang. What I have here is just a schematic showing an example of what one of these reactions might look like. You have some protons, you have some neutrons, they're interacting with one another, and eventually you end up forming some kind of helium at the end of this process. So a few minutes or so after the Big Bang, protons and neutrons had just formed, and the temperatures and densities were high enough that there were approximately an equal number of protons and neutrons. So one was essentially turning into the other and going back and forth through just nuclear processes overall. But as the temperature of the universe dropped, this switching back and forth stopped. So the number of protons and neutrons were then constant. And you can't have free neutrons floating around. At some point, they'll begin to decay. So this is what ended up limiting how long these light elements could form. So you ended up having the formation of hydrogen and helium for this very short period of time, lasting approximately several minutes or so. At least that's approximately the half-life of a neutron before it starts to, a substantial portion of it starts to decay. So when we look at the elements in the universe today, you'll notice that we have, right, these metals that are approximately 2% of all of the elements that we see, and then you have a bunch of hydrogen, and then some helium overall. So today we have about 73% of hydrogen and 25% of helium overall. But if you looked at the periodic table right after the Big Bang, it would have looked like what we see over there. Just hydrogen, helium, and then actually very trace amounts of lithium and beryllium. So something had to happen in between, right, the Big Bang and now to result in literally everything else that you see on the periodic table. So the fantastic thing actually about the Big Bang is if we make measurements of the amount of hydrogen and helium that we see in the universe around us, and I'll talk later on about how exactly we measure the chemical composition of the universe around us, it's actually in pretty good agreement with predictions that we make based on nuclear theory and the like from the Big Bang. So the amount of heavy elements, or actually the amount of hydrogen and helium that we see provides pretty good support for this theory overall. So let's revisit our astronomer's periodic table. We've covered now hydrogen and helium, and now we'll move on to the rest of these interesting processes that have to do with stars and produce the rest of these elements. So a number of elements form inside stars. What I have shown here is a very massive star, several times more massive than our own sun, for example, which is actually a low-mass star, toward the end of its life. And what you see is this kind of onion-like structure present within this star, where you have iron at the center, and then you have shells of different kinds of elements around it, where how heavy the element is decreasing as you move outward until you have helium and helium and hydrogen near the surface. So when elements form inside stars, this is known as stable burning, right? Because you have a very long-lived environment in which, in general, the conditions are not changing very rapidly. So right now, in the core of the sun, hydrogen is being converted into helium, right, through nucleosynthesis. So our star will never end up like this. The sun won't really go beyond forming carbon and oxygen in its core, and then after that, it'll die. But these massive stars have enough energy in order to create all these other things, right? But that raises the question of how do all of these elements that form inside stars actually get out of these stars and into the surrounding universe, right, where they can eventually turn into planets like Earth or even things like us. So one thing you may have heard of in the past are core collapse supernovae. So again, this is not going to happen to our sun, but it happens in these massive stars that are approximately 8 times more massive than our own. So this is that same onion-like star that I showed earlier, except toward the end of its life. And what we're doing here is zooming in on the core. So this core is actually made entirely of iron. And that's because it takes a lot of energy to put into iron for anything to actually happen. So no matter the energy that you get out of, say, fusing iron is not going to make up for it. So this star isn't going to do that. It's just going to be completely inert. It's not going to be doing anything. So what that means is you no longer have fusion occurring. Nothing is supporting the star. So the core is going to start collapsing, which is what's starting to happen here in this second image. Let me get this laser pointer right here. So the portions of this core are not going to collapse at necessarily the same rate. So what you're going to have is the formation of a really dense region in this core. And eventually this will turn into something known as, say, a neutron star, which I will be talking a little bit more about later on. So these outer regions will keep on falling in, and eventually they'll interact with this little baby neutron star that's forming at the center, and they'll end up bouncing off. And this material that's falling in will shoot back outwards, and this will result in an explosion. So there you have it, a core collapse supernova overall. So this is how all of these elements end up getting expelled into the surrounding universe, and then you have these beautiful nebula that we see when we look at the stars overall. So heavy elements can actually be formed in this process since it is so highly energetic. Although I'll be talking a little bit more about that later, but it's likely not one of the most major sources of certain types of elements. So we have another type of supernova that I'll be talking about that also produces elements. So this is called a type 1a supernova. That's just a fancy name. You don't really need to be concerned with it. All that means is it has to do with these white dwarfs. So a white dwarf is something that is left over at the end of a low-mass star's life. So when our sun dies, it's going to expel all its outer layers after becoming a red giant and just leave this hot core left over. That's going to be very small and very dense overall. So you have these two stars that initially start out in a pair and they're just orbiting each other happily. But eventually one of these stars evolves into a red giant and ends up losing all of its outer layers. And then you just have this white dwarf left over. So later on, so these stars may be somewhat different, they have different lifetimes, right? So this one survives a little bit longer. It starts turning into a red giant itself, except this time when it starts losing its outer material, it just doesn't get expelled because this little white dwarf is so dense and has such a strong gravitational pull on the material that it falls onto the white dwarf. And the white dwarf can only handle so much before you start getting a lot of explosions occurring and eventually a supernova, which results in the complete destruction of the white dwarf. But what it does result in is a lot of iron and a lot of elements close to iron in the periodic table. So most of the iron in your body probably comes from something like this that happened a very long time ago. So let's go back to our astronomer's periodic table. So we've covered the formation of all of the elements up until iron at this point, but we still have the entire rest of the periodic table. So these are all formed through something called neutron capture processes. So that's just a fancy way of saying that you have some heavy nucleus or element that just serves as a seed, and you get neutrons that just stick onto them a bunch. And in that sense, they grow. So here you have your initial element, and you have a little neutron that comes and sticks onto it. But eventually, this neutron will decay, and then it'll turn into a proton. So then you have, by definition, a different element overall. So that's the general idea, and everything heavier than iron has formed this way. So it depends on, the number of neutrons that you just have floating around, because in order for this to happen, you need to be in that kind of environment, right? This wouldn't just happen, say, where we are right now. We don't have enough neutrons around for that. So there are two different kinds of these neutron capture processes. One is called slow neutron capture, and it occurs in very evolved stars. So it's slow because the time it takes to capture one neutron, or for one neutron to stick onto this heavy element that it starts out as, say iron, is much, much longer than the time it takes for that neutron to turn into a proton. So it can be about 10,000 years, for example, in between different captures of these neutrons. So this is just an example of one of these evolved stars. It has a carbon-oxygen core that's essentially just the ashes from previous burning that occurred in its center, and it has these shells that are burning helium and hydrogen around it. So in these shells, since you have all of this nuclear activity occurring, you just have a bunch of neutrons that are floating around. And so it's a pretty good environment for the formation of these elements. So one commonly cited slow neutron capture element is barium, for example. So another neutron capture process is known as rapid neutron capture. So, it's just completely the opposite case, where you have so many neutrons floating around that just a bunch are sticking on to the heavy elements before there's any chance for decay to occur. So a possible site for this may be supernova explosions, which I alluded to earlier. So this is an example of a simulation of a core collapse supernova. But the thing is, and it may be that we're not very good at doing the modeling yet, but the estimates that you get on how much of these kinds of elements should be produced by these are not actually in great agreement with what we see in terms of the observations. When you go out and make measurements of how much of these rapid neutron capture elements are out there. It's just not quite the same. It seems to more so require a process that is extremely rare and produces a bunch of these kinds of elements at once. So recently, one particular event has been getting a lot of attention, and those are the collisions of neutron stars. So a neutron star is one of these things that is a product of the evolution of stars. So as I mentioned earlier, sometimes when you have this core collapse supernova and really massive stars, the center turns into this essentially ball of pure nuclear matter. It's extremely dense. It's usually about the size of just, say, I think Manhattan or so, but I mean, it weighs significantly more than that. You wouldn't want any of this kind of stuff around you on Earth, for example. But so sometimes you can get these two neutron stars that form together, or sometimes you can even have a neutron star and a black hole. And at some point, they potentially crash into one another, and you have this extremely high energy event with a bunch of neutrons, now again flying around. So a good candidate for forming these really heavy elements overall. So let's go back again to this periodic table. So at this point, we've covered the elements that formed in the Big Bang, and stable burning in the interior of stars, which occurs up to iron, and then these elements form more so in type 1a supernova, or these supernovae that involve white dwarfs. And then you have the slow neutron capture and the rapid neutron capture that occur in evolved stars, and then potentially neutron star collisions. But how do we know how much of these elements is actually present in the universe around us, right? We seem to have some understanding of the theory, but how do we actually make these measurements? So the measurements of these heavy elements can come from the star's light overall. So what I have shown here is an example of the light that we actually come from the sun. So this was taken with an extremely large telescope on the ground. It's actually in Hawaii. And it just serves as a giant detector, essentially, that ends up collecting a bunch of light. And so you can see what the sun, the surface or the atmosphere of the sun, in a sense, looks like in great detail. So every color that you see here actually corresponds to a different wavelength of light, which also corresponds to a different energy overall. So one thing you might notice is that you have these gaps present, right? These dark regions in the light that you're seeing. And that's actually due to the presence of elements. So I should mention that in forming this image, what the telescope is effectively doing as an analogy is it's like when you pass light through a prism and you separate it into its colors that way. But all of that light is not reaching you, as you can see here. So the heavy elements in the atmosphere of the star are absorbing the light, and so it never reaches our eyes, or the eyes of our telescopes in that sense. So we can actually convert this into some number that represents the amount of heavy elements that we see in the atmospheres of these stars. So again, here we have the spectrum of this star's light. And you may notice that it's a little hard to see, but there is a lack of light right here. So if you sum over all this light and the light, you might have something like this, where this represents, this lack of light right here. And we call this an absorption line. And say how deep this is, or the size of it, corresponds to how many, or the amount of heavy elements that you have in the atmosphere, right? The more you have, the more prominent this is going to be. And it corresponds to some specific wavelength or color of light. So based on our knowledge of atomic physics, we can figure out what that actually corresponds to, right? We have labs on Earth where we can take these elements and excite them and get all the information we need about them, and then compare them to what we see out in space. So these elements imprint a signature in the spectrum of these stars. So here we have, again, this representation of the light coming from stars, where you have wavelength or color, and then just the amount that you're seeing on this axis. And it's color-coded according to all the different kinds of elements that you'll find. For example, very commonly we see things like iron, magnesium, calcium, and silicon. So what we can do with this spectra, or this light that we see, is compare them to models that we make based on our understanding of the astrophysics and the atmospheres of these stars. And then based on those comparisons, we can say how many heavy elements there are in comparison to what we see in our own sun, for example. So this just applies for stars that you can actually see very well, right? For nearby stars, say in the Milky Way, or in very nearby galaxies. But what about distant galaxies? So we can also take a look at their spectra, but we might see something different. So again, here you have wavelength, or the specific color of light that you're looking at, and some measure of the intensity. You see these absorption lines again, because you're looking at a galaxy as a whole, right? It has a very large population of stars, and this is what that represents. But you also have these emission lines that are occurring in these galaxies. So in galaxies, you have these very hot regions that are formed around very massive stars, right? All of this light and energy is coming out, and it's exciting the elements around there. And so these elements are then emitting light. And that's what this corresponds to. So in a similar fashion to the absorption lines, based on the specific emission line, we can make some inferences on what kind of elements these distant galaxies are actually composed of. So one way that we can more directly measure what elements there are in the universe around us that doesn't depend on models, which using a star's light actually does, is looking at meteorites overall, right? So we find a bunch of meteorites around us on Earth, for example. Antarctica seems to be a good place to go. And you can take the meteorite and investigate a part of it and construct something called a mass spectrum, which I have shown here for some particular compound. It's not really important which compound it is, it's just an example. So you can plot the ratio of the mass to the charge when you are breaking apart this meteorite as compared to some measure of the relative abundance. And this pattern that you end up getting when you do this is very unique to the type of compound, for example, or element that you may be seeing. So that will tell you what the meteorite is actually made out of. So when we do this to meteorites, and when we compare it to the most precise measurements that we have of the heavy element composition in the surface of the sun, they're actually in pretty great agreement, which is encouraging because that means that we're doing something right, and we have some understanding of the heavy element content in the universe around us. So now I'll summarize this talk overall. So I hope that you've learned where broadly the elements in the universe come from. So all of the light elements, such as hydrogen and helium, and also trace amounts of lithium and beryllium, come from very early in the universe during the Big Bang. You have a number of elements up to iron that form in the stable environments in the interiors of stars. And just through many processes related to stellar evolution, such as the very violent collisions of neutron stars, as well as the interior of evolved stars overall, and supernova explosions, of course. And we can measure the amount of heavy elements in the universe around us through either looking at a star's light or the light of a galaxy, or more directly from meteorites in the backyard of our own solar system. Thank you. Anyone have any questions? You had your hand up first.
You spoke about some neutron star collisions potentially leading to rapid neutron capture elements. Because
Yeah.
of the work that people have been doing at Caltech, I'm curious if that's been at all of a related interest. You know, to have black hole collisions, what they would potentially lead to if they would be similar.
So my understanding is that black hole collisions wouldn't result in anything similar, since the end product of that would just be some probably larger, more massive black hole. But LIGO is interested in finding neutron star collisions, because that should result in gravitational waves also. And that would be very important for our understanding, for example, of our process, or I mean rapid neutron capture, nucleosynthesis. But my understanding is that they haven't found anything yet about neutron star collisions specifically. Yes?
When I came in here tonight, I had a kind of piecemeal knowledge of a lot of what you covered, but you tied it all together, so thank you for that.
You're welcome.
The question is, could you talk a little bit about how isotopes are created?
So I don't know as much about isotopes, admittedly, but what, for those of you that may not be familiar with the term, it is an element, right, that has the same number of protons but has a different number of neutrons overall. So if you have, for example, the neutron capture process that we were talking about, the difference between an isotope might just be a difference between the number of neutrons that were captured and the number of those that decayed into protons and the like. So we do have an expert in isotopes that will be present on the panel, or specifically magnesium isotopes. But so feel free to direct questions to him. I think that's the best I can do for now. Yes?
I have two things. One is that is it correct to assume that this is theory that's proven mathematically only, not experimentally? And then the second one is, found it fascinating that you mentioned that the building blocks of elements has a decay life, right? So what happens to it?
So for your first question, if I understand it correctly, I think most everything, right, that I've stated here is supported well based on experiment. For example, the experiment would be actually going out there and measuring the amount of each of these heavy elements that we see. And as I mentioned, when you measure the amount of hydrogen and helium and other elements that were produced in Big Bang, and it's in pretty excellent agreement with what we predict based on our understanding of the theory overall. When we're measuring the abundance of, or the amount of these heavy elements in the atmospheres of stars, that's something that's a little bit more dependent on our ability to successfully make models of these atmospheres. So that's something that we could be getting slightly wrong overall. But I think that overall our understanding is always improving, and that we still have a pretty solid foundation in regards to the theory overall. So it used to be formally thought, for example, that core collapse supernova probably produced most of the rapid neutron capture, but as people started to investigate this more, they realized that that may not likely be the case. So sometimes our understanding of this does evolve. But overall, I guess my answer to your question would be it's not just theory. I mean, it is supported by what we see. And yes, observations. And your second question, you were talking about the decay, I think, of neutrons specifically. Okay, so neutrons tend to decay when they're just freely floating, say, in space and the like. So in the example of the Big Bang, about half of the neutrons would decay in a period of about 11 minutes overall. So this would limit the amount of time that you had for nucleosynthesis to occur. When a neutron is a part of an atom, though, it's stable overall. So, I mean, eventually, right, like a proton might be able to decay, such as the protons in our bodies, but it's nothing that we have to worry about because the half-life for that is so absurdly long that it's not even a remote concern. Does that answer your question?
So we don't know that it decays to some unusable form.
So what is it that you are saying? What it decays to some?
You specifically said neutrons, but what about protons?
Yeah, so as I mentioned, we don't need to worry about protons decaying. I mean, things eventually decay, right? Like, for example, the heating source of the Earth is the radioactive decay of potassium, for example. Because the amount of time it takes for potassium to start decaying substantially is approximately, right, the age of the universe. And you have some radioactive activity occurring in the world around you all the time. But I mean, it's not any actual threat overall. It's just a natural process. And overall, all the elements in the periodic table are stable elements, or at least a majority of the isotopes are stable overall. Does that make sense?
The elements are stable, but the building blocks of elements aren't.
Not always if they are not incorporated into an atom and bound. So, for example, like I said, a neutron freely floating will decay eventually, but when it is bound through the strong force, which is just one of the 4 major forces present in the universe, to a proton, it's all good, it'll be fine. But, yes? So I don't think that it's going to do that, at least not in any... What do you mean about the potassium?
You were saying that how the elements are created, the neutron catches and then just decays into a proton, a data particle. Mm-hmm. So how can it do that once it's already hatched?
I see. So admittedly, I don't know the answer to that question. That has to do more so with nuclear physics overall. But I'll keep that in mind. That's something to think about.
Just one more. I know it can be late. Is the neutron created from a proton in terms of binding to an electron? And what actually is that process? How you can convert a proton into a neutron?
So that's something that occurs due to the weak force. Overall, it's called beta decay. When you have beta decay or inverse beta decay, when you have a proton turning into a neutron or a neutron turning into a proton. So again, that's something that's more dependent on knowledge of nuclear physics and these other forces in the universe. So you have, right, the weak force, the strong force, the electromagnetic force, and then gravity overall. So that's something, again, that I don't know the full details of.
Okay, let's thank our speaker, Ivanna. All right, thank you for those of you who stuck around for our panel Q&A. Sorry it was a little slow getting started. So this will basically be an informal-ish discussion and questions from the audience member for our panel. You can ask whatever nominally science-related questions that you have, hopefully astronomy or physics-related questions that you have, and we'll try to answer them. And we'll just go left to right here. First member of our panel, Lee Rosenthal, is a graduate student here. He's happy to answer a variety of questions, but specifically things on supernovae and star formation, some of the things related to what Ivanna was talking about tonight. Eric Mosley is an undergrad here. He's going to be able to talk about galaxies and gravity specifically. Marianne, who's in the corner, who will sit down in a moment, can talk about black holes, X-rays, and neutron stars. Anders Thygesen can talk about, who's a postdoc. Both Marianne and Anders are postdocs here. Can talk about stars, the Milky Way, and I believe you were the isotope guy. He's the isotope guy. And then I'm Cameron here on this side, and I'll be in and out, and I can talk about a bunch of stuff, including simulations, the universe, galaxy evolution, the space program, and such. So go ahead and ask whatever questions are burning in your hearts right now. You have a question?
The four fundamental forces of the universe that you brought up, and I think gravity is sort of self-explanatory, but could you do a quick rundown of the other three real quick?
The four forces of the universe. Who wants to talk about them? I mean, I'll talk about them, but do you want to talk? Okay, Lee will talk about it.
Just a very little bit about them. So gravity, the electromagnetic force, the strong force, and the weak force. So the electromagnetic force is basically, I mean, on a base level, you have static electric force, which is attraction or repulsion between charged particles. So protons and electrons are attracted because they have opposite charges. And then you also will have magnetic forces caused by moving charged particles. So this was first discovered when, I forget who, but some researcher found that wires in his experiment were being pulled together, and he realized it was because that's right. He realized that it was because the current running through the wires is actually just a series of charged particles moving. It's just electrons moving, which will generate a magnetic field, which aligns in a certain way. The strong force and the weak force, I might pass that off to somebody, but in the same way that the electromagnetic force is actually communicated between particles by photons, there are certain particles in the standard model that are thrown between components of atomic nuclei that basically hold them together. So strong force is what binds the nucleus together. It's what binds protons and neutrons together. And the weak force also does something.
From what I understand, the best thing to say regarding the weak force is that it mediates decay and processes like beta decay, like we saw, transformations of particles into other particles.
Did you do the strong force already?
Yeah.
Oh, okay.
Okay, that's good then. Does that answer your question?
Yes.
How did we determine the specific percentage of dark matter, and dark energy?
Can you repeat the question for the recording?
Okay, so the question is, how do we determine the percentages of normal matter, and dark energy, right?
So our current best estimates come from cosmological experiments such as the Planck satellite, I believe. Basically experiments that look at the cosmic microwave background, which is radiation imprint left over from those one of those very early stages in the universe. I think it's the 3-minute stage, right? Or no, sorry, it's the recombination. Yeah, so it's the time of recombination, when you get this basically light imprint from the very young universe at a certain moment, and you can get all sorts of interesting measurements from that. One of which is you can look at basically how uneven the distribution of matter is, because it's very uniform. I'm not sure if this is right. Something like 1 part in 10 to the 6. Yeah, in 10 to the 6 variation in terms of density, meaning imagine this table was completely flat, except every millionth space had a little bump in it, and measuring that will tell you a lot about the distribution of matter, and then you can get a sense of how much of that is dark matter by what's dominated by gravity, and the same thing for dark energy, I think.
So dark energy wasn't dominant at that time, but one way you can measure, so you can get the matter content of the universe by looking at the CMB pretty effectively. But from what I know, today the best way to get the dark energy content is you simply look at how fast space seems to be expanding. You see galaxies around us moving away at a speed that is greater with increasing distance. And that corresponds through a theoretical framework that describes space and time, relativity. That corresponds to an energy density in space. So you can say how much of the universe's energy density is in matter, how much is in dark energy. And it turns out it's about 70% dark energy and 30% matter, and almost no radiation density today. But of course that was different in the past. The various percentages change with time.
Does that answer your question?
Yeah, you in the back?
Why does the universe expand? Shouldn't it like all get closer to gravity?
So I'll take that one. So yes, on small scales, like you don't notice the solar system expanding, right? It seems to stay the same size. Or you don't notice the Earth. The Earth doesn't seem to be getting any bigger, does it? But then once you start to get to large enough scales, there's this extra force that you start to notice. You might think of it as a force. Where things, if they're far enough apart, rather than being attracted by gravity, seem to be repelled, almost. But it's not a repulsion in the sense of if I have two charges together that are the same, they push each other apart. It's a repulsion in the sense that the space between them is growing. And the space between them grows just kind of, maybe the best thing to say is just that's what it does. Like a balloon that by its own nature is inflated. And that's just what the balloon does. So if I have two, basically it's just that on these sorts of length scales of, say, 1 million light years or more, there's this non-negligible growth of space that tends to push things apart. And why exactly it grows, no one really knows that. The best answer right now is just it does, you know. Who was first? You were.
Essentially, there seems to be opposites with black hole versus with the universe too, right? Black hole pulling everything together. The universe is expanding.
I mean, it's not exactly that it's opposite. It's that it's just sort of fundamentally different phenomena, right? Like a black hole is this object that occurs when you get enough matter in one space that there's no possible way for it to hold itself up by any finite amount of pressure. Everything that has gravity requires pressure to support itself. And if there is no finite pressure to support said object, it'll become a black hole. But the universe as a whole, dark energy is a completely different entity, it seems, from matter. So it's not really clear what the connection is, if any. Dark energy, people don't know much about.
Guess I can add a little bit to that. So let me see if I get your question right. It's like basically if we have something like black holes, why they don't kind of win in this sense, and they just like collapse everything together, and we still like see expansion. Is that your question?
Well, it just seems that they're behaving in opposite senses. You know.
Yeah, no, I mean they are. I mean, like we have stuff with like gravity that kind of like pulls things together, and then when we go on larger scales, we will start to see things moving away from each other. I guess like an analogy you could think of is like if you have like you're holding two strong magnets, one in each hand, and when they're close together, they're really like pushing or they're really attracted to each other, but then if you like hold them far away, then like the energy you have in your arms wins over the mutual attraction of these things. So it's just like it's forces that kind of works on, or you can say like that dominates on different scales. I think that's a good. I think that's a good way of, or a useful analogy. So I hope that, helped. Yeah. Sure.
So why does at the beginning of the Big Bang, why did do the graphs show expansion happening in matter nanoseconds and now, and then more recently after that, it happens in terms of billions of years?
Do we have someone here who knows a lot about inflation?
So can I clarify what the question is? So are you asking basically that why was inflation so rapid at the beginning, but now it seems to happen on a billions of years scale, whereas then it happened on a sort of is it still on? Okay. So it's that it's a fundamentally different kind of inflation is really the deal. Today, the inflation that occurs from dark energy, it's modeled differently, it behaves differently, it's thought to have a different source, though that source is unknown. So basically, it's just that it's two different phenomena, right? Like, you can think of, imagine that dark energy is like if the universe was a balloon and I'm blowing up the balloon with my mouth, and inflation is like if I stuck dynamite in the balloon and lit the dynamite, right? Like, my breath and the dynamite are completely different phenomena, and they operate on different energy scales, different time scales. It's just completely different. So is that good?
So usually when we talk about inflation, it's really only this really, really, really short period in the beginning. Like what you said, it's like it takes a fraction of a second, I think. And we've only actually known about that for, I don't know, not that long. So we know that the universe is expanding right now, which is like relatively slow, like you said. And then it turns out that if you calculate backwards, sort of what we think is the size of the universe, if you take the current rate of expansion and you calculate backwards, you don't actually end up with a small enough universe. And there is a bunch of other problems actually with, for example, how do you get the universe to be so uniform, like what Lee said, or what you said about the cosmic microwave background, that we see that matter is really, really uniformly distributed. You need some sort of mechanism to do that, and what people have come up with and what seems to work very well is this concept of inflation, where the universe expanded by it's a ridiculous number. It's like 10 to the 128 or something. It's like a 1 with more than 100 zeros in a fraction of a second. It's not doing that right now, and so what really causes inflation? I never really got that. It's something to do with like fields in a vacuum, and you need exactly the right circumstances, and those circumstances only lasted for a fraction of a second. But after that, you have a ginormous universe that actually works. You actually know how this works.
I was just going to say that nobody actually knows how this works, and people are like, the theorists all across the globe are going like this when you ask them that question. So.
Yeah, and like coming from a completely different field of astronomy, but like the way I typically think of inflation, and I apologize in advance to any cosmologists that might be in the room, is that like inflation is, to my understanding, basically like say a model that was invented to kind of make things fit. It's like we need some sort of mechanism to explain like why a lot of the things we observe, and then people came up with inflation as a way of doing that. So it's basically like it was a model to explain things we were observing. And you may remember a few years ago there was a huge deal, at least inside astronomy, with telescope on the South Pole, BICEP, who claimed to have detected a polarization signal in the cosmic microwave background. And that is one of the few, to my understanding, one of the few things that inflation predicts should be there, so that this is, that it was not, say, built to already explain itself. So that's like a prediction of the theory that we are yet to observe. It turned out that they had observed that that was not what the signal was not what they thought, unfortunately. But if it had been correct, that would have been like the smoking gun of inflation actually being the explanation, because that's a prediction that we can actually observe. Because most other things related to inflation happens at energy levels that we have no chance to achieve anytime soon, to my understanding.
I have one historical note to add about inflation, which was that, so it actually wasn't made to explain all the things it's used to explain. Originally, it was just used to explain why there are no magnetic monopoles observed in the universe. So when I say magnetic monopole, a proton, for example, is an electric monopole. It has, I mean, it has a charge. It's, if you were to draw the electric field coming off of it, things would go out straight. If you put another proton next to it, the proton flies out straight. Electron next to it flies in straight. But there seem to be no analogs in magnetism. There's no isolated north poles. Every north pole has a south pole, and every south pole has a north pole. So why are there no isolated north poles? It was originally made for that, but then it happened to explain a bunch of other things too. You in white shirt in front.
The original observation that caused us to invent, if you will, dark matter was the spinning speed of galaxies was too great for the galaxies to hold together with just gravity. Now, initially there was an explanation that if you fine-tune the gravity equation and then a little component out there for very distant regions, distant radii, you could actually answer that question. But then there were several other observations that were made that fine-tuning of gravity didn't work. And I can't remember what those other observations were.
I can come out, or you can come out, or who wants to come out? Do you want to?
So that's a great question. So for anybody who didn't hear, the question was about dark matter and how it was initially discovered. It's true that one of the first observations that dark matter existed was rotation curves of galaxies. You were saying like the galaxies were, they have a rotation speed as a function of where you are in the disk, and it doesn't follow the profile you would expect just from the matter that you see. The actual first observation, I think, was like of clusters of galaxies that were flying around randomly, and they were bound together when it didn't look like they should be from the amount of mass they had. But then the question was, like, there are theories, most of them like modified Newtonian gravity, that purport to explain these phenomena so that you don't need dark matter, this kind of matter that we don't know what it is yet, we can't see. And like, why is it that those have been refuted? So there are a bunch of observations that refute it. My personal favorite is this thing called the Bullock cluster, which basically shows that like it's these two galaxy clusters collided. Galaxy clusters, right? Not galaxies. Yeah, two galaxy clusters, which means like groups of like gravitationally bound groups of thousands or hundreds of thousands or more galaxies, like basically rammed into each other and came out the other end, and you can observe, and you can like point at this with a telescope and see that the baryonic matter, meaning the gas, the stars, the dust, all the matter that we can see, is in different places than the dark matter. So you can actually see where the dark matter from these clusters are, because it gravitationally lenses galaxies that are much farther away. So one property of like Einstein's theory of gravity is that mass bends light. Very massive objects will bend light around them. So if you have a galaxy cluster, this really massive thing, and then like and then behind it, twice the distance away from us, there's another galaxy. You get these really cool, distorted, magnified images of the galaxy around it in a ring or other shapes. And so with the bullet cluster, what you see is that the dark, here, cluster 1 started here, cluster 2 started here. They both come in, they collide, and then the image we see is dark matter from cluster 2 is over here, and dark matter from cluster 1 is over here. And we see that because of the lens galaxies behind them. And then all of the baryonic matter, so like the stars from the galaxies and the gas, is observed like via, I think, spectroscopy or... maybe you want to...
So the funny thing is actually most of the mass in galaxy clusters is not in the galaxies. It's in this really hot gas that is sort of in between the galaxies. So you don't see it in optical light, but you see it when you look in X-rays, because this gas is somehow, like, it's millions of degrees. So it mainly emits X-rays, actually. So if you look this, yeah. So the X-rays tell you where the gas is, which is most of the baryonic matter. And then the dark matter, like Lee said, is not in the same place. So you know where most of the baryonic mass is, and it's not in the same place as where most of the actual mass is. So I think, yeah, modified gravity has issues explaining that.
Just to clarify, the reason that the baryonic matter gets stuck in the middle and the dark matter passes through is precisely because of the nature of what dark matter is versus baryonic matter. Yeah, we will. Baryonic matter interacts with electromagnetic radiation. It interacts with photons, so it has electromagnetic forces, which ultimately will give you fluid forces. So imagine the stuff in the middle, the baryon, that hot gas, is basically a fluid, and when you throw two blobs of fluid into each other in space, they get there's heating, there's all this messy physics that basically slows it down. But dark matter doesn't interact with light, so none of that stuff happens, and they just pass right through each other. So no modified theory of Newtonian gravity could predict that. And then that guy.
This week there was some news about the supernova that exploded but then kind of didn't explode fully, and I think it was a black hole at core. And I only read the headline, but I really, anybody knew any more news about that? There's an interesting discovery.
Yeah, so I guess you're assuming you're referring to the recent press release from JPL with this star that apparently disappeared. So it's still unclear exactly what has happened here, and it's currently under investigation. But basically, what happened was we have I don't remember the name of the galaxy on the top of my head, but we have there's a galaxy where there's an unusually high amount of supernovae, so massive stars exploding. So it's being monitored fairly extensively, and you had this really bright star of around 25 times the mass of the sun that seemingly has just vanished. It's really, really interesting. So what happened was we saw it was observed in visible light. It kind of started to grow in brightness, and people were expecting it's oh, this is now it's going supernova, exciting, and then that visible light just kind of disappeared really rapidly, and didn't grow as bright as it would have been if it had been a supernova. And right now, there's literally no visible light where that star used to be. I mean, even if you just compare images of the galaxy before and after in visible light, you can see that you can see with your eye that this star is gone. Then if you go slow, so there's been a lot of speculation about what's going on, and one.
What's the time frame, by the way, from one picture to it was there and the next picture was gone?
So that's I think it's the biggest I saw was like a time frame of like a few years, I believe.
Years.
Yeah, which is like super short for astronomy. Since then they're like, okay, maybe this star had expelled its outer layers and created this like huge pocket of dust that was somehow obscuring the visible light. That's a very I think that was the first idea. So then they went and okay, let's go and look in the infrared, because if you have dust that is getting heated by some star sitting behind it, it will re-emit that radiation in the infrared. And the infrared observations basically were also like just like tapering off. So this was happening slower than the optical light, but basically there is no like to have that dust cool so rapidly. You have to come up with some really funky models of how this particular dust around this particular star is cooling to be able to cool it as rapidly as it has happened, if that was the explanation. And then the other more exciting explanation is that what we're actually seeing is a star that has not quite gone supernova and just collapsed directly into a black hole. That would be the first time we've ever seen something like that, because this is the first time we've ever seen something like that. So everyone is like scratching their head, like what's going on? And if that's what has happened, then like since you had this like slight excess of infrared radiation, so there has been like some part of the outer parts of the star that the star has shed before it collapsed, if that's what happened. And then you would have this material starting to probably accrete onto the black hole. And if you do that, you'd expect to see X-rays. And that is ongoing research now to see, like they're pointing like X-ray satellites there to see, do we see X-ray radiation? Because like if we do that, then that's like another telltale that it might actually have collapsed directly into a black hole, and we may have seen this for the first time ever. But this is research in progress, so it's still, I mean, the jury is still out exactly on it, and to determine exactly what's going on and with this very exciting object.
Do people know what the mass of the star before it collapsed was?
Yeah, around 25 solar mass.
25 solar mass. Okay.
I had something about a two-part question about wormholes.
Okay.
And the first was about a theory that I heard a few years ago, and I was wondering whether or not it is or was true, or whether I was misled. And it was that tiny microscopic wormholes appear and disappear all the time, but can't stay open.
Right. Do you want to? I think black holes on your thing. Oh yeah, Marianne has black holes on hers.
So I just spent a day at JPL 2 weeks ago explaining about wormholes, more or less. So the answer is that the question is about wormholes, how microscopic wormholes would open and close, and that's the question, right? So I think these are very theoretical constructs, and if there were microscopic wormholes opening and closing all the time, we couldn't see them. So personally, I wouldn't be bothered about them. So there are these, every now and then you get these theories that like every black hole has a white hole on the other end, and that forms a wormhole. I think, as far as I understand, the idea is more that if you would have something like a wormhole which would somehow connect to parts of space-time through, I don't know, you'd have to make a tunnel through space-time, then it would look like a black hole. I don't think the theory says that every black hole should necessarily be a wormhole. It's just that, yeah, if you could make something like a wormhole connecting one piece of space-time to another bit, then it would look like a black hole. And I would personally not risk my life trying it out. Yeah, and so even in theory, they're very unstable, so they would collapse.
The second part of my question was, regardless of whether or not that theory is true, why don't we see more wormholes? Or do you not know that?
Yeah, so this is the thing. If wormholes would exist, they would be hidden inside black holes, and we cannot look. I mean, we see black holes. We even know sort of how to make them, more or less. I don't think most of those black holes would actually like form wormholes. I have no clue how you would make a wormhole, but the problem is that if you hide a wormhole inside a black hole, there's no way we're going to tell it's there, because nothing comes out of a black hole. We don't know what's going on inside a black hole, and we can't know because nothing, no light, no information ever comes out. So it's very easy to make lots of theories about wormholes because we won't ever be able to check it.
And in addition, so part of the whole wormhole theory is that this is a connection between a black hole and a white hole. And there's never been any observations of white holes that are just spewing out energy and matter in the same way that's described by this theoretical construct. So there isn't a lot of evidence for it. That's not to say it doesn't exist, but to date, astronomers haven't seen any evidence for that kind of a structure. That's a good, yeah, that's well put. The only way we could detect a wormhole is in a place that we can't go or detect anything inside of. Yeah.
So recently there was another detection of gravity waves from LIGO, and I was wondering, because maybe it wasn't making sense to me, but if they were saying that this was caused from two singularities or two black holes merging. So my question is, if we have one singularity and another singularity, does it, when they collide, does it form just one singularity or just two separate singularities? What happens in that process that causes?
Who wants to cover it? Yeah.
Yeah, so the question is about the recent LIGO detection. So LIGO detected a third or fourth, depending on who you ask, gravitational wave event, where now I think it's like a 20 and a 30 solar mass black hole that were merging into one approximately 50 solar mass black hole. And so the question is, what happens when you have two singularities that merge? And it does become a single singularity, because yeah, that's what gravity does, basically. So we don't see the singularity itself, right? I mean, the black hole is actually has a size, or the horizon beyond which we cannot see has a size of a couple kilometers. So you have these, first the horizons will merge, and this is what actually causes, so this is pretty cool. This is what causes the exact shape of the gravitational wave signal. It's called the ring down. So basically you get this, initially the horizon of the black hole is a little bit deformed because it's two black holes. So they form some sort of dumbbell, and then they eventually merge into a single spherical horizon again, but it rings down. That's what it's called, the gravitational ring down of the black hole, and that's what causes the signal. So that was one of the questions for these gravitational wave things: are our theories correct? And so far, it seems to match general relativity pretty well.
Would you say that black holes take in matter and turn it, spew it out into energy?
No, I would say black holes just take matter and then it just stays in the black hole. They don't do anything with it. It's just.
What about Hawking radiation? Is that?
Well, but does anybody wants to talk about Hawking radiation?
It's more of a drizzling out. It's not really spewing out. A very, very small amount of the energy and the mass that's in the black hole is kind of seeping out slowly through the Hawking radiation. So
You do have an in and out.
you do have an in and out, but it's the difference in the magnitude of how much stuff is going in versus how quickly it's evaporating off is a factor of like 1 trillion times or something. Like a black hole, I mean, it depends on the environment and the mass of the black hole. But we'll say a black hole, like the black hole in the center of our galaxy, the Sagittarius A star, is what's 1 billion, 4 million? Okay, 4 million solar masses. Trouble with the connection. 4 million solar mass, so 4 million times the mass of the sun in terms of its mass. And it's accreting matter, not a ton, but like, actually, I don't know what's the accretion rate. Was that low? Oh, okay. Well, okay. Supermassive black holes in galaxies, some of them are accreting matter, a solar mass a year, or more, like AGN quasars. Yeah. Yeah, accretion rates are crazy. Whereas the evaporation rate due to Hawking radiation is usually tied to the surface area of the event horizon of the structure. And the evaporation rate, Leo, can you give me any numbers on this? It's like...
It's totally irrelevant for any astrophysical black hole.
Yes.
It would be longer than the lifetime of the universe.
Times a billion or something. Yeah. So it would take longer than the age of the universe for a black hole on that size, or even the size of our own sun, to evaporate entirely. So to get rid of one solar mass would take longer than the age of the universe. The only time it matters are for very, very tiny ones, like microscopic black holes, which have never been observed, but we presume exist due to certain phenomena in the universe. And they could evaporate rather quickly, quickly astronomically, less than the age of the universe timescales. But I don't think there's any kind of observational constraints on Hawking radiation. But this is a plug. The Astronomy on Tap speaker in a week and a half, Ron So, is going to talk. I was talking with him today. Is going to talk about Hawking radiation of microscopic black holes. So, bring your question in a week and a half and a beer, and hopefully these questions will be answered. Yeah, so, sorry, that was kind of a long-winded. None of us explicitly work on Hawking radiation, so it's a bit of a challenge. The younger gentleman back there.
So if you were hypothetically to be able to make a micro black hole in a particle collider, would you be able to observe Hawking radiation? And how long would it take for the black hole to evaporate?
Good question. Yes, potentially if you had the ability in the particle collider to create a black hole, you could... It's challenging, right? Because as soon as you form the black hole, there are going to be a number of processes that are going on with it. One of which is Hawking radiation should start occurring, so it should start evaporating. There's another process, and that is because it has mass, it obeys gravity, it's going to fall towards the nearest large mass, which is the center of the Earth, so it's going to start, falling towards the center of the Earth. There are a bunch of different processes going on. It would depend on the size of the mass of the black hole, how quickly it would evaporate, and there are tables that you can look up or equations that you can look up that will tell you how quickly one will evaporate in the time scale, or like what time scale it will evaporate based on its mass. I don't happen to know them off the top of my head because I don't work on that, but you can look this up. And it would be a competing effect between how quickly it could accrete matter as it's falling through the Earth towards the center of the Earth versus how quickly it's evaporating due to Hawking radiation. There's actually a really good science fiction book called Earth by David Brin, I believe is the author, that explores this whole idea. The short answer, I'm not going to ruin the plot. It's an interesting book, but don't freak out because I think it paints a picture that looks a little doomsday-esque because it's a science fiction novel, but it's an interesting premise for a book. Do you have something else?
Yeah, so just to add like a slight curl to that, I seem to recall that back when they were gearing up the Large Hadron Collider in Geneva, this was like there were enough people that had raised concern about like, oh, well, we're now creating like microscopic black holes, and then what's going to happen once we start colliding particles to these extremely high energies, and so apparently enough people were concerned that someone actually made like a theoretical study of assuming that with the energies we have here, we do create a microscopic black hole. How quickly would that evaporate? And the answer was that if they were created, they would evaporate so quickly from Hawking radiation that it would not be a concern at all. Yeah, so that was yeah. I remember like seeing that mentioned at some point, like quite some years ago.
What are the characteristics of Hawking radiation
So, yeah.
He's given talks. An additional member of our panel, Leo Stein, who's also a postdoc here, who does a bit more on Hawking radiation.
I study black holes. I know this. I do this for fun. Yeah. So people have calculated the properties of Hawking radiation, and it depends almost completely just on the mass of the black hole. More or less, the wavelength of the radiation that's coming off is approximately the size, is proportional to the size of the black hole. So very, very large black holes are giving off very long wavelength radiation, which is super, super low energy. So you can state it in terms of a temperature because the spectrum of radiation that's coming off, you know, how much long wavelength, how much short wavelength, is almost the same as a black body spectrum. So you can give this thing called a Hawking temperature that characterizes the radiation. And the temperature is inversely proportional to the mass of the black hole. So very, very large black holes have very, very low temperatures. In fact, I think I remember that for all astrophysically relevant black holes, the Hawking temperature is so ridiculously tiny that it's colder than the temperature of the cosmic microwave background, which means that actually all astrophysical sized black holes are receiving more radiation from the cosmic microwave background than they're emitting in terms of Hawking radiation. So even if you got rid of everything else in the universe and you only had black holes, those black holes would still be growing because they're receiving cosmic microwave background radiation too fast, rather in relation to how much Hawking radiation they're emitting. Once black holes get sufficiently small, then you could say, oh, the energy, the temperature is so high that instead of only emitting light and gravitational waves, it would actually start producing massive particles. It would be producing neutrinos, and it would be producing electrons and protons and neutrons. But basically, you would have to have a black hole whose diameter, I mean, this is kind of off topic. If you want to do a homework exercise, you can go and convert what is the Compton wavelength for the mass of an electron and figure out what size black hole that has to be to actually produce electrons just by having a black hole sitting there. But you'll find out that it's a ridiculously tiny black hole. Hope that answered your question.
So, in the first place, you don't really observe the black hole itself, right? Because the black hole itself is black. So what we do observe is the effect it has on its environment. And usually, when we look for black holes, we look in X-rays because there's a lot of things in the universe that emit an optical light, and it's really hard to find out which ones are black holes. But what you get is so we don't usually observe single black holes just sitting in space and doing nothing. What we see is black holes that are like eating mass from usually a companion star, or in the case of supermassive black holes, just from gas that's floating around. And so matter falls towards the black hole and it forms a disk, and the disk gets really, really hot, and that emits a lot of X-rays. Actually, if you look at the universe through an X-ray telescope, most of the things you'll see are accreting black holes or neutron stars. So that's how we find them. And then if you do look with an optical telescope, you may actually see the star that is feeding the black hole. And this is how we learn a lot of things about black holes, like their mass. If you observe the star going around the black hole, you can actually use Kepler's laws, the same for planets going around the sun. For stars that are going around a black hole, you can actually calculate the mass of the black hole.
If someone left their cell phone in the women's bathroom stall, we have it up here. Anyway.
Going to the beginning of the universe, you have the fundamental particles. Why does the Higgs boson appear to be the most prominent out of all of them?
why does the Higgs boson get a lot of attention? I think maybe just because it was this particle that was predicted for around 40 years, and people spent a long time building the experiments to finally have a large enough energy to confirm that it was really there. And it was the last outstanding prediction of the Standard Model, which hadn't been directly confirmed until, what was it, 2012? Yeah. But, right. I don't know.
Yeah, so also, and well, I guess another, at least for me, like another reason why the Higgs boson was such an exciting discovery is that if you look, I mean, if you go and look at the Standard Model and on the particles of the Standard Model, then to my understanding, the Standard Model predicts, like if you don't have the Higgs boson, all the particles in the Standard Model should have no mass. They should be massless. So it's like the Higgs boson is like or the Higgs field, I suppose, but the Higgs boson is like we have photon that is like carrying the electromagnetic force. We have the Higgs boson who's carrying the Higgs field that gives other particles mass. And it's like, because like we know the particles have mass, but we were yet to figure out like what's the transmitter of mass, and that's the Higgs boson. So it was really exciting to finally see that it's actually there, because okay, then we have an understanding of why particles have mass. So I guess that was another reason why people were extremely excited about the Higgs boson when it was discovered. So the short answer would be, so the question was like if we have something that goes into a black hole, if we can somehow remake it, and you can say like once something has passed into a black hole and like beyond this, basically beyond the event horizon, as far as we're aware, it's like there's no way we can't get it back out. So it's like if it goes in there, it's like it's gone from like say like the part of the world that we can interact with. So we can't bring it back out. It's stuck in there. So yeah, that would. So I guess the answer would be no. We can't really bring stuff back out from a black hole once it's there, unfortunately.
So there was kind of a big debate in fundamental physics for a long time, because in classical physics it doesn't really matter if stuff falling in, if the information is lost from it. But once you throw quantum mechanics into the picture, then it's a big problem if we lose information. It kind of makes the theory of quantum mechanics doesn't work anymore if information is lost. Our best understanding of like the rules of quantum mechanics, one of the fundamental pillars of quantum mechanics is that information is never destroyed. So for a long time, people had, this is still a paradox that's not explained, that black holes might be destroying information. And we have to come to grips with that and understand how to salvage the theory. Like the theory is in danger if we really think that information is destroyed. So some people think that Hawking radiation is slowly returning the information of all of the stuff that fell into black holes back to us. Other people disagree. It's still a debate, and there isn't really a consensus on it. If you asked a bunch of people that study this to vote on whether or not they think black holes destroy information, I think it would be 50-50.
Guy in the gray in the back.
So, based on what you're saying right now, I have two questions now. So, what information is theoretically being destroyed? And then maybe the easier question is, how do you determine the temperature of a black hole? Or maybe that's not an easier question.
So, isn't it just all forms of information pertinent to the matter?
How technical of an answer do you want? Oh, sorry, I have to repeat the question. So the question is, what exactly is the information that's being destroyed, and how can we measure the temperature of a black hole? Is that right?
Yeah, and the information, I mean, like, how it relates to mankind as far as, like, that's the filter. That's my, like, when you say information is being destroyed, I think, okay, like, the internet is one, and computers is ones and zeros.
Yes, good, very good.
So what do you mean by information to a non...
Yeah, no, that's exactly the same thing. So, you know, we take a hard drive, there's a bunch of basically magnetic domains on it that we lined up with tiny little magnets, and they're representing zeros and ones. And if you take that hard drive and you throw it into a fire, then that information is lost as far as like our ability to read it back with a computer. But in principle, it hasn't been destroyed in a quantum mechanical sense. So in quantum mechanics, there's another sense of zeros and ones, not exactly just like the alignment of these magnetic domains, but still a quantitative sense of is there information there or not. And it's kind of like whether or not all of the probabilities, so you probably know that quantum mechanics is a theory of stuff happening in the universe that has probabilities. It's not deterministic, it's probabilistic. So one of the rules is that all of the probabilities still have to add up to 1 and for the math to make any sense. So in a sense, for information to be destroyed is that the probabilities stop adding up to 1. In the processes that we understand, like taking a hard drive and throwing it into a fire, we understand how, like, you know, the burning logs are emitting gases, and that's making light glow, and it gets really hot, and then it melts the metal. We understand all of those processes well enough that we can say for sure that there isn't any information being lost there. But the mathematics of stuff falling into a black hole makes it look like the probabilities stop adding up to 1, and that doesn't make any sense. The mathematics just doesn't work at that point anymore. Does that answer your question?
I think so.
Okay. And for the temperature thing, so for astrophysical black holes, we'll never be able to directly measure it because they're so ridiculously tiny, and basically the rest of the universe is too hot to be able to measure them. We can calculate them from our understanding of Einstein's theory of general relativity, and it just depends on the mass and the spin of the black hole.
Guy in front.
So why isn't there a consensus that the Hawking radiation doesn't return information back to us?
Okay, so the question was, why isn't there a consensus that the Hawking radiation is returning information to us? Okay, so one of the problems is that in quantum mechanics, instead of having bits like we have in computers, we have qubits. These are the quantum versions of bits. Information in quantum mechanics is the fact that certain qubits are not independent of each other. They have to do with each other. They're entangled with each other. That's the quantum mechanical version of information. So if you start out with 2 qubits that are entangled with each other, and you get rid of the entanglement by throwing one of the qubits into a black hole, that would be destroying the information. So if you want information to be returned to us in the Hawking radiation, then that means that the Hawking radiation that's coming out actually has to be entangled with the qubit that you held onto that stayed outside of the black hole. The reason why there isn't a consensus is because there's already something else that qubit has to be entangled with of the Hawking radiation that's coming out. So Hawking radiation comes in something called Hawking pairs, which is actually when the Hawking radiation is spontaneously formed at the event horizon, one Hawking pair comes out and one Hawking pair falls into the black hole. So the Hawking radiation that's coming out is already entangled with something that's falling in, but you want it to be entangled with that other qubit that you kept outside of the black hole. And quantum mechanics has this property that's called monogamy of entanglement that basically says you're only allowed to entangle a qubit with one thing. So if you want to resolve the paradox, then you both want the Hawking radiation that's coming out to be entangled with the qubit that you held onto, but it's already entangled with its other partner that fell into the black hole. So it seems like it doesn't make sense anyway because it's violating this thing called monogamy of entanglement. So basically, every time you try to resolve this paradox, you're just moving the bump in the rug somewhere else. It just wiggles around at you. So probably to resolve it, we're going to need to figure out how to make gravity itself quantum mechanical, and people have basically been working on that since, you know, a few years after general relativity was invented, and we still don't know how to do that. I think that I don't think I know any more about qubits coming out of black holes. I basically said everything I knew. One recent paper on this topic was written by Sean Carroll, who is a professor here across the street, and he's going to be giving a lecture here in a few months, right?
Yeah. So yeah, Sean Carroll, I handed out the flyers for our lecture series, but it doesn't have the people or the titles, because I have the people set, but not the titles. Sean Carroll's giving one of our lectures in, I believe, August 11th. The August 11th lecture will be, is it 11th? No, August, what was it? Oh, I think I messed that up. I think it's actually August 11th. Oh, shoot. Well, the August date will be Sean Carroll, and you can ask him, because he works on this stuff. So, whereas none of us really do.
So the question is, are neutron stars called neutron stars because they are made of neutrons? And if so, where did it come from? And the answer is, actually, we still don't know yet. We think they are probably neutrons. But there are a lot of theories about strange stars that would be made of strange quarks, I think. I don't know. There's a lot of theories floating around about what neutron stars are actually made of, and the answer is that we don't know yet. But we're getting more and more... It's pretty hard, actually, to tell anything about what's going on inside a neutron star, and the best things we can do is try to measure the radius and the mass, because every separate theory about, it's called the equation of state, like what is a neutron star made of, and every separate theory has its own predictions for the relation between the mass and the radius. So as soon as you start measuring masses and radii for neutron stars, you can, in principle, tell at least which ones are wrong. And it's actually really hard to measure the radius of a neutron star because it's about 7 miles and they're really far away. So we're starting to get there. I think people have discarded some of the more outrageous theories, and it looks like they may actually be made of neutrons, but we still don't know yet. Actually, one of the experiments that's going to help us tell this is called NICER, the nuclear something. It's an instrument that's going to be at the International Space Station, and it was supposed to launch yesterday, but the launch was cancelled because there was a thunderstorm at Cape Canaveral. So now if everything goes right, fingers crossed, they'll launch it tomorrow, and it should be up at the International Space Station soon after. And it should start observing this summer. So we're hoping that might help us tell that. And the reason why we think they're neutrons actually is because, so white dwarfs are still made out of protons and electrons, and they're sort of like separate. And in a neutron star, the density gets so high that actually the electrons and the protons are forced to basically merge into neutrons. And then all the while, because neutrons, like Ivanna said, aren't stable, so they will decay. So it's basically an equilibrium between neutrons decaying into protons and electrons, and then they're being forced together again by the pressure, basically. Does that answer your question? Right, how do we measure the size of a neutron star? So the best thing we can do at the moment is, like I said, when we look at black holes, when you want to look at black holes with an optical telescope or with an X-ray telescope, what you really see is the matter falling into the black hole. Neutron stars do the same thing. Matter falls into the neutron star, it forms a disk, and what we try to do is measure the size of the inner radius of that disk, and that assume that that is more or less at the surface of the neutron star. It's pretty hard. Sorry? Yes, that too. There is something about sometimes. So when neutron stars accrete matter, so there you get a layer of basically. So neutron stars are made of neutrons, right? But the upper layer, if you dump mass onto a neutron star, that mass will mostly be like protons, hydrogen, or whatever the donor star is made of, but usually it's hydrogen. And so you dump it onto the neutron star, you get this layer of hydrogen. And at some point, when the layer gets thick enough, it basically ignites and starts to do fusion. And this causes X-ray bursts. And when that happens, the outside of the neutron star sort of expands because it heats up. And you can sort of measure that too. And that also tells you something about the radius.
Another thing that just constrains sizes of neutron stars in general is there's a class of them called pulsars, and some of them seem to be rotating on a millisecond type of time scale, so like a thousandth of a second for it to turn all the way around. And since matter can't move faster than the speed of light, that tells you if you just assume that what is pulsing is on the surface and it went around once, if you said it was going at the speed of light, that gives you an upper limit to how big it can be. Yeah, you.
Do we know anything about the electromagnetic fields of black holes, and is it possible to detect from a distance electromagnetic fields? And is it possible that the electromagnetic field of black holes was holding the galaxy together?
No. Okay, so the question is about electromagnetic fields of black holes, and I can tell you it's not holding the galaxy together, just because on such a large scale, electromagnetism just doesn't matter that much. So the electromagnetic force is on small distances actually a lot stronger than gravity, but because there are so many free protons and electrons everywhere in the galaxy, if you have a really strong electric field, you would just start moving the charges around until they cancel each other out again. So you don't have, well, that's not true. There are magnetic fields, large-scale magnetic fields in the galaxy, but they're fairly weak. So neutrons...
Things are weakened, right? Because,
yeah.
Because we're saying that gravity is stronger than electromagnetic force.
Well, the gravity is more important, just because there's a lot of mass. And so if you would have strong electric fields on a large scale, it would just start moving a lot of charge around, and it would eventually, those charges would cancel each other out again, right? Because you need, for example, a large positive charge to create a strong electromagnetic field, but that would then attract lots of negative charges, and because there's like single charges floating around everywhere in the galaxy, they would just eventually meet each other again and cancel each other out.
So to just add on to what Marianne's saying, gravity is just an attractive force. It's just pulling things to Anything that has mass is pulled to anything else that has mass. It just works as attractive. Whereas the electromagnetic force can both be attractive as well as repulsive. And so those can, as she was saying, can cancel out. And you can get the attraction and repulsion canceling out, so there's no net force. Whereas gravity doesn't cancel out. It's just additive. It just keeps getting bigger. And so when you have a large mass like the galaxy, there's no way of canceling that. You're always having this attractive force that's holding it together. Whereas even if you have a large amount of charge, positive charge or negative charge, some of it's going to cancel out because you'll get the negative charges going towards the positive charges, as Marianne was saying. Sorry, I didn't mean to take that.
And so I think in principle, black holes could have a charge, and then they would have an electric field. But so in practice, in the universe, that just doesn't happen because it would get cancelled out immediately.
Yeah, yeah.
So I always.
I mean, everything has some kind of electromagnetic field, right?
Yeah, no hair.
So actually, there's a theorem about black holes. I don't know if this is right or not. Maybe you could tell me. But that called the no-hair theorem, which basically means like there are only like a few parameters that can characterize a black hole because you don't have any information about what's inside. So it's mass, spin, and charge. That's it, right? So 3 numbers characterize a black hole, and a result of that is that you can't have magnetic field lines going into a black hole. Is that right? Yes. So any magnetic fields near the black hole would basically have to swerve around it, because at the event horizon they would have to be parallel to it, because you can't know whether there's a magnetic dipole inside the black hole or not. So you can't have field lines going in. I think that's it.
Well, 2 last questions, because we're 1 minute until 10 o'clock, but we'll keep going. You guys get your hand up for the others.
I had another question about the speed of light. Just continuing that brought up a couple of questions ago, and it's not so much like what happens when you approach it, but why things can't approach it.
It's more or less just a property of space itself.